Welcome to the Ask the Experts New Boring Solutions webinar, hosted by Cutting Tool Engineering. And our expert panelists from Big DAISHOWA and Rigibore are here with us. The subject of today's webinar is about new boring solutions technology, particularly automating some of this technology and the processes that go on. And the following video that I want to show is a good encapsulation of what we're going to be talking about here today. It's a video that Rigibore has put together that sort of presents the challenge and some of the technology that they've come up with that's helping to solve some of these challenges. So let's take a look at that video.
Have you ever wondered if there's a technology that allows micron-precise modifications to the cutting edge to be made at the touch of a button, with unrivaled ease of adjustment in the boring operations? Here is when Rigibore's Active Edge comes in to save the day. Active Edge is much more than a tool. This auto-compensating device employs wireless technology to execute micron accuracy adjustments without requiring the participation of an operator. Tool adjustments can be made outside the machine spindle, such as the ATC, automatic tool changer, thus allowing subsequent machining operations to continue while the tool is being adjusted for the next component, ensuring minimum downtime, guaranteeing that non-productive time in the operation is removed. Micron accuracy can be easily attained and maintained automatically in boring operations using Active Edge tools, which follows a straightforward and easy procedure. Active Edge tooling allows a close tolerance bore diameter to be maintained throughout the boring operation without the involvement of an operator's intervention, thereby helping your business to enhance output. Get yours now.
Okay, so I just want to quickly introduce our moderator today, Keith Jennings. He's a former owner of Crow Corporation, a family-owned shop down in Texas, and he's also the longtime manager's desk columnist for Cutting Tool Engineering, and he's agreed to be the moderator today for our webinar. On our expert panel is Anthony Bassett, the president of Rigibore Inc, and Matt Tegelman, the senior product specialist at Big DAISHOWA Inc. So with that, I'm going to throw it over to Keith to begin our webinar.
Very good. Glad to be here today and looking forward to this. Well, we have a series of good and interesting questions, and we're going to start with this one and address this first one to Matt. And that would be to help us identify and discuss some advancements in this boring technology that are helping our shop floor machines transform industrial production. That's a big question and a lot going on there, but that's an important one because I know the technology has advanced a lot and y'all are at the forefront of that. What do you think about some of that, Matt? How can we help these shops? Or what can we do with them?
First of all, good morning, everyone. In this case, I really think the advancements have come from outside the industry in the form of smart devices that can communicate with one another. As this technology has become more common, the availability, cost, and size of the components used in these devices made them easier to implement in tooling applications. In the case of our EWA boring head, we're talking about smaller actuators, servo motors, and signal transmitters. So much like consumer devices in your house where your refrigerator can let you know if you need to put a new item on your shopping list. We're using this technology in our boring tools to talk to the machine control back and forth to make corrections on diameter.
Interesting.
The other major advancement is in communication with the use of Bluetooth or Bluetooth Low Energy in this case. We use this version because of the low power consumption required and the limited data that we're actually sending back and forth between the boring head and the control unit. It's common technology that's currently available in most smartphones and tablets, so we can also use these devices to connect to the boring head to preset it, make manual adjustments to the size if necessary, or to check its adjustment history. Finally, the Bluetooth Low Energy interface is robust to interferences. So as more and more communications occur in the machine environment, we can ensure that the communication to the boring head is secure and the tool adjusts correctly.
Very good. Okay, interesting. Okay, well, our next question, thanks, Matt. And our next question is to Anthony. And what are some real-time benefits of automated boring bar systems that cutting tool suppliers and manufacturers should embrace to stay competitive? Oh, I'm sorry. Oh, okay. I'm sorry. That sounds good.
Okay. Good morning, everyone. Yes, we're identifying and discussing advancements. I mean, in reality, we are looking at the product quality, improved product quality, reduction in scrap, improved productivity, consistency in the bore size, and the reduction in the need now for skilled operators required to do this work. So as you can see here, our system is set up with a cartridge, and we can then communicate to the cartridge via RF. So here's your boring bar, and it's self-powered. So you have the yoke here, and then you have a battery pack which goes into the yoke here. And then this is the cartridge that actually sits in the bar. So this is the part that actually is doing the movement. So all the parts that do that movement, the actuator, the measuring device, everything that sits inside there is sat inside that cartridge. This allows us then to be able to, on bars like you can see in this picture, if there's damage or something occurs, we can then take this cartridge out, put a new cartridge back in, and then we can upload a calibration table via our ActiveNet software, and then this will actually the bar can go back online, and it's easily put together with actually the customer. So adjustment factors, once we send an adjustment to the tool, that adjustment factor is sent by RF. So it's very low voltage RF. And we send that to the tool. It handshakes with the tool. The tool communicates back, knowing that we've got a handshake. And then an adjustment factor is then sent to the tool. So that adjustment normally takes about 2 seconds per micron, roughly, to do that. And then once it's completed that, it then sends a signal back to the machine telling it that it's ready to go online. Batteries, in this case, we produce those. Their estimated life is about 2 to 3 months. So this section of the tool here, this is what we call the yoke assembly, and this is where all the electronics are. So electronics sit in here. The RF transmission receiver, obviously the batteries go inside that, and then that's the bit that communicates with our interface on the machine tool and then back to the tool. So and then here we are using it. It can be available on any machine spindle. So we can pop in, from HSK to Cat 50s to whatever. So, the end of the day, I think it boils down to the fact that, from a precise measurement, we can then send a precise adjustment, knowing exactly how far we've moved to the cutting edge, and that returns that signal back and lets us know that we've actually done that. So that's really how our system works there.
Interesting. Okay. Very good. Well, thank y'all for that. Okay, we'll move and bring up question 2 to Anthony once again, for him to start this one. And that, again, what are the real-time benefits, you think, of automated boring bar systems that cutting tool suppliers and manufacturers need to embrace and adopt to be competitive and remain competitive? What do you think?
Yes. So I'm bringing this slide up, but I'll just talk a little bit before we go into this slide. I think the main benefit here is a consistency in the adjustment. So basically, what we're doing is, instead of taking what would normally be the usage of a boring tool, where you realize that the boring tool needs to be adjusted, the machine is stopped, or the tool is removed, and then you adjust it manually to that position, either using a digital readout or taking it to a presetter. We're basically linking that back, and we're using a form of measurement that's measuring the bore, and then that measurement is then being transmitted back to the machine tool. So that sits in the machine tool, and we interrogate that measurement, and then we give that an upper and lower limit from that position. So that upper and lower limit can be determined by the user, and he can decide how far he wants that out. So, he might want that limit to be small, he might want that limit to be larger, depending on the type of product he's using or the tolerance required. And then we are sending that precise amount to move that back to either nominal or above nominal, dependent on whether he wants that tool to drift down and then get to its bottom limit, where it then adjusts back up. And then you are then adjusting basically for wear on the insert. So that element has always been, I think, in a way, sometimes hard, to adjust the boring bar. There's, you end up having oversized bores, you get scrap, and so on. So we see that changing because we know exactly how far we're moving it, and that gives us a much better component at the end of the day. It gives a much better quality of component at the end of the day, and also, where we'll talk about CPK, and having a better CPK, and for customers who are, especially aerospace and people like that, who are looking at obtaining a really good number there, we see that CPK value creep up and creep up and creep up, which is where we want to be, and basically, get a really good part off the machine right first time. So that's how I see that development going on.
Very good. Very good. And same question to Matt.
Yeah, let's just we're going to just show a quick video here,
Okay.
and this will give you an idea of how it works, and what we do to make that work. So if we could just run the video, and I'll just talk over it. So right now, basically what we're doing is we're showing the tool, and the tool is machining a 50 millimeter bore. Okay, so it's boring that 50 millimeter hole, and then we're using the probe. Probe is going in, doing the measurement, standard Renishaw probe, Renishaw software, and now we can see that that size is 4 microns under. Okay. So what's happening now is we send that signal from our interface, it meets the machine, and while that's going on, we're then roughing out the bore that's the next one in line. Once that measurement has been completed and it's fed back to the machine, telling it's now back online, tool changes that tool back into the spindle, and then we're going in and we're cutting that finished bore size again. Next, the probe will go in, it'll measure the bore, and then that allows us now to be back to that size. So these are, it's micron accurate. We end up with 1 micron on diameter accuracy here. So in this case, multiple cutting edges, 1 bar. Here we've got tools that are basically used for huge diameters, right up to 3-4 inches in diameter, and then the line boring tool, so we can independently adjust every single tool that's on that line bore, so keep each journal the same, and then smaller diameters are available as well. So it just gives you that bit, and then obviously we're conforming to that 4.0 industry standard.
Right. Okay, very good. Very good. Matt, could you address that same question about the real-time benefits of automated systems to stay competitive? What would be your approach?
Okay. I think these systems are, very important, but overall a much smaller piece of the whole manufacturing process, becoming more automated and providing real-time feedback along the way. Most data these days is not generated by people doing data entry. It's done by machines logging their activities. So I think it's important for shop supervisors to have real-time data as far as what they're producing, how long they'll be running a specific job, and knowing what's coming next to better control their inventory levels on tooling, on materials, and every other thing that's related to their manufacturing process.
Mm-hmm.
So for the closed loop boring and going beyond that, Industry 4.0 tools talking with each other, as we get more familiar with these cycles, we need to look at what else we can connect to in the machine shop environment, which devices may be included in that loop to help streamline the process. With boring tools, obviously tool presetters are a common one. They help get the tools to the starting point for the test cut. And afterwards, when the tools are being inspected on CMM equipment, can that information be transferred to the machine as well to help further the adjustment process and eliminate steps with measuring cuts and stuff like that? And then other information that could be tracked eventually in the tool to be sent back for further evaluation is temperature data. This can help determine if a tool is cutting efficiently. We want the heat from the cutting force exiting through the chip instead of going into the tool. And finally, vibration analysis is critically important. Possibly one day we can even incorporate vibration compensating devices which can be adjusted in the tool while it's cutting to make sure that the tool is cutting efficiently.
Interesting. Very good. Okay. Thank you, gentlemen. On to question 3. And this will go to Matt first again. Can you discuss the impact and importance of an automated boring system capable of automatically compensating for those diameter changes without removing the tool from the machine? What do you think about that and the benefits of that?
Well, first off is repeatability. One of the most important things that we stress, even with our manually adjusted heads, is the importance of making the final adjustments in the machine spindle. Whenever you try to set the boring head out of the spindle, you're introducing the chance for the spindle and taper interface repeatability to affect the final boring size. So anytime that you can make that final adjustment in the spindle, whether it's manually or automatically, you're eliminating one more place for error to creep in. Usually not as much of an issue for shorter tools, but as tool assemblies get longer and longer, that run out is magnified over the length of the tool. This is actually an example from our EWE digital heads, which are still manually adjusted, but it shows that you can remotely see the adjustments that are being made to the boring head, and not just the incremental change, but also the final output diameter. With tolerance information included, the operator also has a visual confirmation with the color of the numbers to ensure that the bore is within the tolerance window.
Okay.
And now when we look at our closed loop program with our EWA, we now have 4 components that are present here. We have the machine tool with the control, the probing system, and we're not locked into any specific probe type. Any probing system that gives information back to the machine control can be used for this. Our EWA software, in this case, which is run on a separate industrial PC that's connected to the machine control, and this is what's communicating with our EWA boring head, which is the fourth piece. So the adjustment information is given from the machine control via the probe to the computer running the EWA software, telling it how much it has to adjust. Once the adjustment is made, the boring head gives a signal back to the control, confirming that it has made the adjustment and is locked and ready to cut. This tool does not do any adjustment while it is cutting. It is strictly for straight line bores. It's not a U-axis tool, but it does have a generous adjustment range. So if you have a part that has several different bore sizes that fall within the range of this boring head, you can do multiple bore sizes with a single head. This head is also more or less a standard tool solution in that it has our modular CKB tool connection, so we can adapt it to most common spindle types and sizes, as well as being able to use our modular extensions to increase the length of the tool using this technology.
Interesting. And Anthony, same question to you. The importance and impact of an automated boring system and the compensating for the diameter changes.
Yeah. Well, basically, again, it goes back to the fact that, we're looking for a tool to give us better precision, better quality, improve productivity, because we're not taking the tool away to the machine tool setter. We're not taking it to the presetter to make it a very fine adjustment, and then we're taking it back. Obviously Matt said that, as soon as you remove it from the machine tool, you end up with an accuracy between, this machine spindle and the taper in the presetter, which can cause you errors. You were really trying to get to the fact that, once we've got a gauge in place, and that gauge can be anything. I mean, we're talking about offline gauging. We could be talking about direct, plug gauges, which are in the machine tool. We could be talking about a probe system, and so on. At the end of the day, that is the key factor. If you're going to close the light, shut the lights off, and have a closed loop system, you've got to guarantee that the gauge data that you are interrogating is absolutely 100%. Okay, because as soon as you don't, and if you have that situation with, say, a probe, the probe hasn't been qualified, or somebody hadn't done what they should have done, then you end up with error. And the active edge boring tool will only do what you tell it to do. So if you set down the upper and lower limits to plus or minus 3 or 4 microns, as soon as it jumps out of that, it's going to go to that position. And another thing we've noticed, especially with automation, is that using probes, sometimes you get dirt on the probe and so on. And then within a production environment, if you just go, okay, well, I've jumped outside the upper or lower limit, I need to send a compensation to the tool. It transmits to the tool moves. There is error in those probes. So you could have plus or minus 2 microns or whatever in that probe. And then you end up with sending signals to the tool, and the tool's moving up and down. And then you end up with this situation. So what we want is basically a situation where we are getting a sawtooth type situation. And we tend to look at, okay, if we're using a probe, we want to have at least 2 values, consistent values, which are either outside of that limit. And then once we've got that, we know then that making that compensation is going to bring us back to that nominal value, and so on. So, these are the things that it does. I said it before, the CPK gets better. We've got more uptime because we're not in a situation where somebody's having to go into the machine and make an adjustment and feel confident about making that adjustment. Obviously there are very good manual systems out there that, at the end of the day, sometimes, especially with the slide that I'm showing on here, if you've got a component, wind generation part, something like that has an extremely large diameter, this part is extremely expensive, and you cannot afford to scrap it. Similar in aerospace, you've got to know that you're going to cut that part correctly. And obviously a lot of time is wasted in shops where guys are concerned, there's a high stress level by making that adjustment and making sure you're not going to scrap the part. So with Active Edge, we use what we call a two-step process, where we back off the tool and we cut the part undersize, or if it's an overturning tool, similar to the top right-hand picture that you can see there. So we turn the head around and we can cut ODs as well as IDs. That we cut that undersize, we send the measurement system in, it measures the part, it tells us now exactly how much stock is left. And then from that, we make that adjustment and then we cut that part to size. And the good part about that is because, a lot in old school type of situation, you'd creep up on that size. You creep up and you creep up and you creep up, and then you cut it to size. We don't want to do that. We want to use the insert geometry to its best advantage. So by backing it off, we're taking a decent cut. We're not rubbing the insert, and we're getting a consistent size. And just moving on. So, you've got here in our Nexus development head here, not developed, but this is available. We use this in lots of different companies out in the field right now. So you've got a self-contained head that can go on to a course adjustment system. It can be moved around, it can be turned around, and it is self-contained in its own right. And obviously then if you've got a number of those in a tool, every single one of these has a unique ID. So it's always handshaking with that unique ID, knowing that that's cutting a 375 mil diameter. It knows that that's in the fact. And the machine tool control program is the controller, and it's calling those components as and when it's needed through a series of macros. Okay?
Very good. Interesting. Yes. Okay, very good. Okay, and we're going to, we have one more question to ask. Okay. I would like to go ahead and let the participants know we're going to address our last question coming up with Anthony and Matt. And if you have any questions to add or would like to pose to these gentlemen, it's a good time to go ahead and start. And we will bring those up and address those questions and answer those at the end of this last segment. Okay, we have our final question, and we will start with Anthony again. And that is, what has been the reaction from shops who've adopted these solutions? And did a lot of your floor personnel, was they well received, and or is it a challenge maybe getting in there and training? But what are the reaction from some of these shops and their staff who've adopted this technology?
Okay. Yes, it is. It is. In some cases, it's challenging. I think for a lot of places that once you have this forward thinking, and you start utilizing, a closed loop system, a lot of operators and shop floor supervisors and so on have always been wary. If you introduce a gauge to something which is cutting a critical diameter, you
Right.
might put a probe in there, and they'll probe the part, and then they'll take the manual gauge and they'll go in with the manual gauge just to make sure that the probe's reading the right thing. And that's a challenge. That's a challenge to get people to be comfortable with the fact that you're taking that away from somebody. And that's also another element. You're taking away a job which they were trained to do, or in some cases. But, we start moving into a realm now in life where we don't have those guys. Those guys have either left, they've retired, there's no apprentice system. People, it's difficult to adjust some of these things, and again, there's the stress of making sure we're not going to scrap apart. But what we've noticed is once we introduce this system into a shop, and you've got the time to show what it will do in a production environment, and we've sorted out, gauging is good, everything is good, and then they're seeing these bore sizes staying so consistent. Every part. In some cases, we might adjust every single part. They were never doing that before. They would let it drift and let it drift and let it drift, and once it got to danger zone, they'd adjust it because nobody really wants to do that. Okay, so that's taken a lot of that situation away, and once it does, and once it's accepted, we then see more sales. You see more sales from that. You also see people word of mouth going out there and saying, okay, within maybe a group of companies, they get to know what that is, and so on. So we get to a situation where as you can see here, there's numbers of different tools on the picture here. These are tools that we've supplied to lots of customers, and and they're all different sizes. They're all doing different things. So once you get to that point, it is accepted. And what I'd like to just show you right now is just a quick case study, which we did in a power generation customer, where they were making very large connecting rods, and we produced these tools that were actually closed loop, 2 spindles, and this whole thing was robotized. So there was robots loading the parts. Everything there was no guy inside it whatsoever. And when the connecting rod came out, it went to an external measuring system. It was put on that external measuring system. The bores were checked, so 2 plug gauges go in, super accurate. Information was sent back to the machine tool. It was stored in the machine, and then these tools were taking that and then adjusting automatically from that. And here we see some of the bore sizes. So this is actual production. So you can see here, sometimes you get a little a spike every now and again, but you can see the consistency in production. And we start hitting CPK values of nearly 3, which is unbelievable. And you don't scrap a part. These parts just don't get scrapped any longer because we're constantly doing it. And then obviously, as the operator sees, that we've got machine tools are such now that you can program into wear rates on inserts and so on, and it alarms out, so they can then tool change out, put a sister tool in place. That tool goes into place, and unique ID is then uploaded into part program, and it continues. So that just gives us some idea of if we're getting some sort of 40% increase, and you can see another thing here. You can see the nominal value here that the customer decided here. He wanted that to be nearly 5 microns above that. So he's looking at trying to make parts that are actually a little above that size. So when it comes to assembly, the assembly was easier based on information that they were receiving from the assembly line. So their ability to be able to move the upper and lower limit independently and allow that to happen, it gives them great flexibility. All right?
Interesting. Yes. And same question to Matt as we wrap up this segment. What has been your reaction, and what have you observed from some of your shops and customers that have adopted your technology?
Okay, well, first off, our EWA program is not officially been released yet. We're in the final stages of testing, but we do have some key end user partners that are helping us conduct the final stages of testing. And one of the results of that was conducting this repeatability test based on a newer closed loop cycle. We went into this with an example like this, and sorry, I don't have a picture of the actual part that they're producing, but this particular part had 4 different bore sizes. And our first recommendation out of the gate was to, do a semi-finished pass with the tool, measure each bore size, and then do the final adjustments. Well, they wanted to streamline that a little bit and whittle down some time. So they suggested, could we possibly just measure the first bore size, and then using the absolute value scale inside the head, then just take the first finishing cut, measure that, and use that information to offset, let the head make the final adjustments for the rest of the cuts. So they set up this test and ran a batch of parts, and the results on the table at the right show the output for those 4 different bore sizes. Now, hole 1 was the only one that was being measured consistently. So as the insert wore down, it was being measured probably not even every part, every 4 or 5 parts. So the variation comes in the fact that the size was only being tracked after a certain number of parts, and you had more variation in that first hole when it was being measured continuously. So it was valuable feedback to us to be able to, going forward, recommend this kind of cycle with less measurements, taking less time, but still lying within the tolerance range for these particular parts. Now, if they wanted to tighten up the standard deviation for that first hole, we would just add more measurements in the boring tool cycle. And now I've got some video footage. Unfortunately, it's not doing multiple sizes. It's more similar to what you saw with the Rigibore video, but we are doing a semi-finished cut, probing the part, measuring, sending a signal to the head to adjust, and then taking a final cut and remeasuring.
Very good. Very good. Well, at this point, I don't see any audience questions just yet.
There is one here. I'll post it now so that you can see it. So,
Very
can you
good.
switch between English and metric adjustments?
Yes, I see that now. Switching between English and metric. Anthony, would you be able to start with that
either one of you?
Yes.
Yeah, I mean, all our system is measured in metric, so we don't have any English adjustment on that at all. It's all done in microns,
Okay.
and that's the way the system is put together.
Very good. Matt?
With ours, you can reconfigure the EWA software. I mean, it's going to be set up to whatever the machine tool is dealing with. If it's if the dimension, if it's running in English mode, it's going to use, the software is going to be set up to use inch dimensions. So either way.
Okay. Any other audience questions at this point?
Yeah, here we go.
And I see that from Randy, and he's asking, will these tools be off the shelf or made to order? Matt, what would be your response to that one?
The EWA will be off the shelf. Right now, the size that we have shown in the video and in the presentation is a size 68 based off of our CK6 connection. So that would start at roughly 2 5/8 diameter up to, with 3 different insert holder options, that's taking you to a little over 5 inches in diameter. And then we have large diameter components to extend that range larger. Currently in development is also a small diameter version of this head, similar to our 112 series, where the boring bar is mounted in the center of the head. That will have a range of 10 millimeters to 54, so about 394 up to a little over 2 inches. So those will be 2 standard heads.
Okay. Interesting. Thank you. And one other question to Anthony first. How much stock can automatic boring systems take per pass?
We can take up to, if we wanted to, we could take a millimeter depth of cut if we needed to on our system, but that's not normal. So, normally we'll be taking 20 thousandths, half a mil. That's what we normally leave for boring. Obviously, in some cases, if we're cutting, different materials, it could be Inconel or, aluminum or different stuff like that. It'll depend on the material type and what it will do. But yes, you can take a bigger depth of cut. We don't really advise that. We advise just going with the normal standard, what is suitable for a finish boring pass. This is not a roughing tool. It is a finish operation. So we're looking at normal finish passes.
Okay. Matt, any follow-up with that?
Yeah, I would agree with that. 20 thousandths probably on the very high side. If it's an extended length tool, you're going to want to, use a smaller nose radius and probably cut that stock allowance in half, if not even more. But very light cuts. I mean, obviously not, taking skim cuts and rubbing, but you want a good clean cut. But certainly, it's not a tool that's going to be used for anything other than, tight tolerance work, small depths of cut.
Interesting.
Could I just go back on the previous question we had? We were
Yes.
talking about off-the-shelf items.
Right.
Just so you know, a lot of the stuff that we produce right now, we produce dedicated tools, either with one cutting edge, multiple cutting edges, and that's what we do. We have standard product. Those cartridges are standard. They fit in there. The yoke assemblies are standard product. So we build that stuff up and build it into built off-the-shelf orders. We have in development now the boring head system, which would use standard boring bars that would go into the head that you could adjust different sizes. And we're also working on right now a coarse and fine adjustment system where we'd be able to have a coarse range for a number of heads that will be stock, and then the customer will be able to move that to whichever position he's doing, and then the active edge tool would take over as normal, doing that closed loop situation. All right.
Okay. Thanks for that. Any other audience questions at this point?
There are no new questions that have come in. I do want to just note that somebody had asked early on if there was an e-certificate that would be available after this webinar. We don't offer any, certificate for having been through the webinar, but if that is something that people are interested in, provide me some feedback. Either email me or send me a text and let me know if that's the sort of thing that you would like from these webinars. It's something that we could do if there's enough interest in that.
Right.
So with that, let me ask Anthony. We've got this other video, and it's kind of an addressing the installation. Kind of an overview of the installation process. Is that something you think could be worthwhile to set up, and then I can show that video?
I mean, we can certainly do that. I mean, it'll give us a pretty good idea of how we install the system on the machine and how it gets done and the simplicity of it. So yes, we can do that.
There is no denying the advantages of Rigibore's Active Edge boring tools. Active Edge tools have the unrivaled ability to automatically make adjustments from your measurement data with micron accuracy, and installation is just as easy. For this, you're provided with antenna, Active Edge tool, AEI, and an AE cable. In the CNC machine, there's an I/O port, wherein we connect the input and the output cables to communicate with the CNC. There's also a 24-volt wire to connect to the positive node of the port, and a 0-volt ground wire to connect to the negative node of the port, which will power the AEI from your CNC. Don't forget to connect the CNC output wire and the input wire as shown here. Active Edge supports Siemens, Fanuc, and Mazak machine controls covering most CNCs. The antenna is then installed near the work envelope before being connected to the cabinet with the network wire. This enables wireless communication with the Active Edge tool. All of the wires will now be connected to the AEI in their appropriate jacks as displayed on the screen. The AEI and antenna LED will take around 15 seconds to light up after being turned on. Before going on to the next step, make a list of the 100 user variables, inputs and outputs that you've selected for Active Edge processes. Once this information is received, the Rigibore engineer provides you with the custom subprograms, which you can include in your production program to make automatic adjustments in code. And that is when you need to put the customized macros into the appropriate folders on the machine control. It's a good idea to tune the AEI to CNC right now. To do so, run the program 8500. The AEI LED begins to flash blue while the tuning is in progress. Allow 5 minutes to accomplish this step. Once complete, the system will output the file 8510 SPF into your AEI, and the LED will turn back to green. When complete, connect the other end of your AEI's network cable into your network or directly into your PC. This is when you install ActiveNet and add the AEI to the software. Once that's done, all you need to do is open the AEI system folder and transfer the 8150 SPF subprogram to the memory stick. In ActiveNet, you can also monitor every step, check tool statuses and battery levels, and maintain your Active Edge firmware and cartridge library. All that's left is to copy the 8510 SPF subprogram onto the memory stick and paste it into your subprogram folder on your machine control. Now the installation is complete, you can use your Active Edge subprograms in your main production program to fully automate your boring process with micron accuracy. You are now all set for Industry 4.0 and lights out manufacturing, giving you a cutting edge in the market. Get yours now.
Very good.
So we did have one more question come in. Is there anything you wanted to follow up before we move on? We got one more question that came in.
No, I'm good.
Now, let me show this next one.
Okay, this last question is, what is your Dell on your special tool? And how about addressing that one first, Matt?
The audio is breaking up a little bit. I'm assuming we're talking about delivery on
Correct.
this.
What is your delivery on your special tool? Correct. It was abbreviated. Sorry about that. But yes, that's it.
Our EWA tool is being introduced at IMTS later this year, and we should have the first batch of actual production heads available in Q1 of 2023.
Okay.
Our standard delivery on tools right now is anything between 6 to 8 weeks. So on a special product, once we've signed off on the print, you can get an Active Edge tool in about 6 to 8 weeks. And then obviously there's installation. So, we have to set up, we have to connect to the machine control and so on. So that's our normal delivery on specials, is 6 to 8 weeks.
Okay, very good. And another question. Will this be compatible with Haas mills? That
I don't think we've worked with Haas yet as far as their control units, but it's certainly something that we could look at down the road. I don't see why not.
very good.
Yes,
Anthony,
it is. Yep, it is.
it is compatible.
Yep.
Okay. I think that's all the questions that have come in so far, and we can give it another minute or two. Is there anything that you would like to ask Keith before you?
Kind of one thing that,
or any observation?
yeah, one thing that came to mind that I wanted to ask both very quickly was when you get a new request or inquiry for some technology or product, is it common or typical you would have to send a technician or staff there to install gear and or train, or is a lot of this shipped to them, and can they take care of that part with their own personnel and y'all work with them remotely, or what would be a typical installation or process or training process? And do you normally have to send people on site to do that, set that up? And Anthony, how about you first?
Yeah, I mean, what we've noticed. I mean, we've been doing this a while now, so this product has been out 6 years, and it's developed over time. And I think initially we would be normally on site setting that up.
Right.
As time has gone on and technology has made it easier, and I think COVID and the pandemic pushed this into another realm.
Right.
It pushed us to a point where we could do this remotely. So an installation, once we would send the parts to the customer, and sometimes initially in Fanuc and Siemens style controls, normally that's maintenance can do that work, or they need to have somebody come in from the machine tool dealer to help with that. Mazak is a different thing entirely. You have to get an option for Mazak to run some of this stuff. So a normal Mazak machine doesn't come with that stuff. You have to get it from them. And so there's an active edge option that they sell, which goes through that. But yes, I think initially it was that way. I think also it depends on the size of project, and helping these guys through it and getting them comfortable with running a different system. I think that is sometimes where you need to be on site, because it's not normal for them to do this. We're doing something very new and very different, and as we know, it's taken a long time for people to get comfortable with that. Over the years, we've seen this product increase and increase and increase. Years ago, it wasn't that much, because I'm not sure that people were comfortable with that. But times are changing. You don't have people. You can't get people to work for you. You can't get skilled guys and so on. So us as tooling suppliers need to change, and we need to offer ways to do this. And nowadays, I think what we're seeing is we can install this and not actually be there. It's got to a point where it's quite simple, and you could see from that video how easy it is to connect that. You could have a video conference and do that quite easily without even putting up. The days of having to get in the car and drive places, those days are diminishing. So that's what I see from my side.
Okay, Matt, what would be kind of a approach from your company? Is that something you would address on site frequently, or not necessarily?
For us, just getting started launching this product up front, we're going to have people out in the field helping with installations. Now, to what degree, I think depends on how this is coming in as a project. Is it something being done on legacy machines? What is the technical competency of the end user? Do they have a strong in-house knowledge of working on the machine controls, or is it a turnkey project where a machine tool company who maybe we've worked with setting this up previously, are they the ones bringing it in, and in which case would probably require less in-person time from us, but for the first few installations, we're definitely going to have people in the shop helping them set this up and get implemented. Because it doesn't just stop with the getting the tool to talk back and forth. We've got to do cutting tests and make sure we still got to dial in the mechanical part of it. It's not as simple as, okay, the tool adjusts, it's going to work fine. We've got to help them establish speeds and feeds and all of that stuff as well.
Interesting. Okay. And one other question has come in from Brady, and that is, can you explain how the smaller boring head will work being adjustable from 10 millimeter to 50 millimeter?
So that product is going to require more accessory products, more boring bars and insert holders to cover that range. It won't have the same stroke as the larger head. So I would say at this point you can probably count on the smaller head as being more of a dedicated one size per tool situation. You're not going to do a large adjustment going from 10 and then cutting another bore that's 25 millimeters, because that's going to drastically affect the balance of the tool assembly. So in that case, I would advise that you're probably going to need multiple heads if you have a part that has a bunch of those different bore sizes.
Okay.
So yeah, the short answer is a lot of accessories. It's not going to be the adjustment of the head covering that whole range by itself.
Okay, very good. Anthony, any thoughts come to mind on that?
Yeah, I concur with Matt. When you're talking about smaller diameters, you're down to 10 millimeters. We see that being, dedicated bars between 3 millimeters to 25 millimeters. That type of thing would be normal. And then after that, you would have a range after that, which would be a smaller range. And again, you have to be careful, because you're moving, a mass. And then as you have smaller diameters, your spindle speed is faster. You've got inherent balance issues and so on. And then we're talking about a boring head here that is adjusting to microns. The reason it's doing it is because the tolerance dictates that. The part quality will dictate that. Out around will be dictated by that. If we've got a very tight tolerance, then you can bet your bottom dollar that everything else is going to follow, and there's going to be consistency through that reasoning. So you have to be very careful on what you try and gain, and so you can possibly lose. On the other side, where you're not maybe keeping the bar absolutely round. So as Matt said, balance is a critical issue here.
Right. Very good.
Well, I think that we're just about out of time. There are no other questions that have come in. I want to take an opportunity to thank Anthony and Matt, Rigibore and Big DAISHOWA, for participating in this webinar. You guys have been great. And thanks for understanding, working with me. Speaking of COVID, I've been dealing with COVID this whole week, and it is not easy. But thanks to virtual reality or virtual meetings, we're still able to pull this off.
Yep.
And again, I just want to thank Anthony and Matt for your patience working with me and your diligence. And Keith, thank you so much for moderating this event.
No, very interesting, and thanks to Matt and Anthony. Yes. Looking forward to seeing you guys maybe at IMTS.
Yeah, thanks, guys, and appreciate the opportunity to get with Matt here and show people what the technology's like now.
Yes, indeed.
Yeah. Thanks for the platform and the opportunity to talk about our new products, and
Very
Okay,
good.
and that wraps up this webinar. For anyone who might just have been joining us, this is the end of the webinar. It will be available on demand to view it in its entirety after about an hour or so. So a link will go out to anyone who was registered for this event and couldn't make it for the entire presentation. Again, thank you all, and have a great rest of your day.
Thank you.
Take care, guys.
Thank you.